Okay, so we're going to start with a very kind of abstract theoretical section about random variables and independence of random variables and talking about events and mutually exclusive. But now we're going to go, well, it's still going to seem quite theoretical, into something a bit more useful for you. And what we're doing here is used in the field in engineering. Statistics is very, very important, and hopefully I can get that across to you in your third assignment, which I still, as of 13th of November, still have not really thought about. Okay, so think about a machine filling a very fine powder into containers. So you can think about bags of cement if you want. So let X be the fill put into the next bag. X is usually not a whole number, even if you use units of kilograms and say it's a 30 kilogram bag of cement. I don't know, is that a good number or not? It's not going to be exactly 30. It'd be 30 points something, whatever, or 29 points something, whatever. Due to the variability of the machine, the value of X is not certain. It doesn't give exactly 30 kilograms every time. A continuous random variable is a random variable that can take on any value in a continuous range. So what I mean by that is between any two values, there's another one. It's even a bit more than that, which I probably don't really need to get into it, but like it could be 30 theoretically, it could be 30.1, 30.4, 30.48, 30.462, and like you can just keep adding numbers here and it can take on all these possible values theoretically. Now of course this number then will have trailing zeros forever and ever and ever, this kind of thing. So any number on the number line or between two numbers in the number line. For a continuous random variable, there's just too many possible outcomes and all the probabilities are zero. So thinking about your bag of cement, the probability that it is exactly 30 kgs is zero. Even if it's designed to fill it 30 kgs. Let me explain this. So 30 kgs, like, oh, surely that can happen. Well, really it has to be 30 kgs and 0 grams and 0 milligrams. This is all to be 30 kgs and 0 micrograms. Now maybe it's possible to get it to the nearest microgram, but after that I can't remember what next is, like pico or something, 0, 0, 0. And eventually when it gets so small, the numbers are essentially random. So I suppose this is the point. After here, the numbers are essentially random, you know what I mean? So if it's going to be exactly 30 kgs, this next number has to be a 0. That's a 1 in 10. And the next number as well. So that's 1 in 100. And the next one, 1 in 1,000. 1 in 10,000. 1 in 100,000. And it has to... And that number, that probably keeps getting smaller, that all of these numbers forever and ever and ever are infinite, are 0, when each digit is equally likely. It's basically not going to happen. So the probability that the continuous random variable is equal to some specific number is 0. So we're not going to look at those probabilities. So look, in a particular population of males, the following distribution of heights. So this relative frequency would be, so it's like 3%, for argument's sake. So 3% are under 150 centimeters, 10% in here, 20 in here, 0.33 in here, 20% in there, 10% in there, and 3% are over 200 centimeters. Okay, so we could summarize this data in what's called a relative frequency graph. So let me give a belt off drawing this. I've lost my sharpener. Here, look, it's alright. So I'm just going to draw some lines and then we'll go from there. So I got 3%. It's probably something like, go across there like that. I've got some 10% action. Go across there. Some 20% action. Go across here, and then some 33% action, which is something like this. Right, and then we're looking at, well, I'm going to assume that the less than 150 is actually 140 to 150. God, what am I doing? 10%, and then 160 to 170 is 20%. Sorry, I'm being a bit of a dope here. There's that. Then it goes up to 10%. Then it goes up to 20%. Then it goes up to 33%. We'll get there eventually. Then it comes down here. Jeez, very slow. And I'm going to assume that the bigger than 200 actually just goes up to 210. That's not necessarily true, but that's what I'm just assuming. Okay. Now, one of the things I've done here actually is I could have made this a bit better, and I'll explain why. So these numbers on the left, that's fine, but the way it really should work is the following. These numbers should be smaller. So I'm going to divide all these by 10. So this is 0.05, 0.04, 0.03, 0.02, 0.01. I'm going to explain why I did that. So if I do that, I've done it in a specific way. I've done it so that the area in each of these regions is equal to the probability. So the area of this thing here, or probability / proportion, the area here is 10 by, this was 0.003, so this gives me 0.03. This is 10 by 0.01, which gives me 0.1, which is 10%. The base is 10 by the height, gives me 20%, and this one gives me 33%, 20%, 0.1, and 0.03. And this becomes what's called the relative frequency density. And it's probably good that I do that. Okay, so we see this kind of a thing. Now, what if we make the bins narrower? So rather than looking, so this is actually the same as this, is it? Who knows? This is 1, 2, 3, 4, 5, 6 bins. This is 5 bins. So this is, so say the number of bins is n. So you got 5 bins, 6 bins. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 bins. More. Oh, it's written there. Oh, these are widths. So it's 5 bins, but the width of them is 20. Width here is 10. Now it's going a bit further on than this one. And here there's the bin width is 5 and the bin width is 2. And you see the shape that you're kind of getting. And if you keep making more bins, so this is same as n getting big. So what I'm saying is if you want to take more bins, then the bins get narrower. You're getting this shape, this bell-shaped curve. And we assume that these populations kind of come, so the population of males, for example, here, comes from that if you keep making the number of bins bigger and bigger and bigger, of course this will kind of be a smooth curve, and this is kind of, we're assuming what's going on. So we speculate, and usually often we assume that there is a probability density function, so this is the same as relative frequency density, probability density function, that can tell us not only what proportion of people have a height between 170 and 180, as this thing did, so the proportion have a height between 170 and 180 is equal to the area under the curve between those points. That what we can do with this thing is not just between 170 and 180, but between 170 and 172 or any other interval. So what we won't be thinking about is what's the probability that, say, the cement is exactly 30 kgs, we'll be thinking instead, what's the probability that it's between, say, 29.9 to 30.1? What's the probability that it's in a range of values? And this is what we will work with. I was going to say something there and I forget what it was, so I better just drive on. So here, yeah, here's one. So what we should see here, 33% of heights, total area is 1, because what's probably that your height is between, say, 0 and infinity? It's 1. And the relative frequency is proportional to this thing here. So if we want to find, say, for example, the proportions of people that have a height between 170 and 172, which should be the same as the probability that if you take a random person, if, say, 5% of them are in that height, and you take one person at random, the probability that they're between those two will be the same as the proportion in the full population. It's given by the area under the curve. So we're thinking now in terms of a person chosen at random, and h is their height. The probability that the height, I remember what I was going to say now, is between 170 and 172 is equal to this area. Now the thing I was going to talk about was, does it matter if I include the 170 or not? So if I include the 170 or not, does it make any difference? And the answer actually is no, and I'll just write up here why it isn't. We'll just look at the probability that the height is, say, greater than or equal to 172. So what's the probability that someone's height is greater than or equal to 172 centimeters? So what we can do is we can break this greater than 172 centimeters into two events. It's the probability that the height is equal to 172 or greater than 172. This is a little bit tricky now what I'm doing. So that's what this means, greater than or equal to, greater than or equal to. And then from our theory, we know that these events are mutually exclusive. They can't happen at the same time. You can't be taller than 172 and have a height of 172 centimeters at the same time. And when you have mutually exclusive events, the or means plus. And what is the probability that your height is exactly 172 centimeters? Well, it's 172. Actually, yeah, 0.00000. Eventually you get down to a certain thing. Now, there's issues here about how do you even well define someone's height, like hair and everything, but just forget about that. Eventually, when you get down to a certain precision, the numbers are essentially random, as before. And the probability that this is your height, and as those zeros go on forever and ever and ever, is exactly equal to 172 is 0. There's an interesting thing, by the way, where 171.9999999 is also equal to 172, but we don't need to go into that. So this probability here is equal to 0, and so we find that we're just left with the probability that your height is greater than 172. So if I talk about, in this context, greater than or equal to with a continuous random variable, it doesn't actually matter whether you include the 170 or not. Okay. So many examples of continuous data are unimodal. So unimodal means it's got a single peak. So it's peaked or bell-shaped, and symmetric. So if I draw a line here through the peak at 175, it looks the same on both sides. So that's symmetric. It can be shown to be of a certain form. Such data is called normal data, and we say is a normal distribution. By and large, data with a dominant average, with deviations from the mean. So this this peak here is the average or the mean, really. well, it's funny. We'll talk. We didn't really talk much about mean and all that, but the mean. It's hard to talk about the mean of this kind of thing. So what you want to think about the mean is if you take a load of people from the population and you take the average of their heights, you should expect it to be this dominant average, the 175. So in that sense, it's the mean. The mode is the most likely height. Now it doesn't make it's easier to talk about mode in one of these where maybe everyone's height is given to the nearest centimeter, and then the height that occurs most often is the mode. But it doesn't really carry up so much, but we're just going to say the peak is the mode. That's what the modal there means. And then the median, you might remember, separates the small from the big. And if it's symmetric, the mean and the mode and the median are all the same. It separates the taller than average from the shorter than average. Yeah, but this thing, when I write average here, it doesn't really matter, but we're thinking of it as mean. So if you have data that has a dominant average, so say for example, now the funny thing with the bags of cement is that they're probably not going to design them to have a mass of 30 kgs because they're probably just as likely to be slightly bigger or slightly smaller, and you might get people giving out that there's a lot of light bags. So instead what they actually might do is they might design the process so that they give you 30.1 kg on average. So imagine that the 30 kg bags actually have an average of 30.1 kgs. So when they're filling those bags, that's the average and that's the dominant average. Most of them are kind of close to 30.1 kgs, but the bags are just as likely to go slightly over or slightly under, and there's no real bias between them. And then that kind of data where you have a dominant average and then errors either side is typically going to have this normal distribution. So by and large, data with a dominant mean average with deviations from the mean, so it's differences from the mean, justly likely to be positive or negative, tend to have this shape. Now, there's something called the standard deviation. Now, calculating the standard deviation is a little bit messy, but I think what we're going to say is something like this. So imagine these are the heights. Now we're going to talk about standard deviations in a further lecture, but it's basically a measure of how spread out the data is. So take a large number samples. So if this was a population of say billions of people, which it isn't, but imagine it is, take a very, very large number, and then the standard deviation of the sample converges as n gets bigger and bigger and bigger to some number. It's basically a measure of how spread out the data is. So for example, I think a good analogy which I used to talk about was kind of in rugby teams. So back around 10 years ago, the Irish rugby team, you had like shorter players like Ronan O'Gara and Peter Stringer, and especially tall players, say Malcolm O'Kelly, I forget how young he are. Anyway, it was very tall and very short, but actually now you tend to have players being, in general, kind of all taller. So even Conor Murray, who, like Peter Stringer, used to be 5'6" or something, and Conor Murray is 6'2". So what you have now is, if you look at the Irish rugby players, they all have a kind of a more similar height. The height isn't really spread out, whereas 10 years ago the height was very spread out. And there was a more extreme version, is the Georgia rugby team. They all looked like the same person. Like I don't mean they looked the same, but they had the same body shape. So they kind of all had the same height. So that was a small standard deviation. So standard deviation measures how spread out the data is. In terms of quality, like for the cement bags, you'll want the standard deviation to be small. You'll want them all to be kind of similar mass. Okay. Well, anyway, for the normal distribution, approximately 2/3 of the data is found within a distance of 1 standard deviation. So 2/3 of the data is about 1 standard deviation away. And I think about, is it 95% of the data is within 2 standard deviations. There are 2 bits of information which summarize the data. The mean average, this bit, mu, mu. I write mu, I don't know, mu. I don't know what's going on there. Anyway, so this is the mu, and then the standard deviation is the width of this. in a certain sense. And so when we want to write down a particular normal random variable, we'll write down n mu sigma. So this is normally distributed, the average is mu, and the standard deviation is sigma. So maybe if we kind of go back here and estimate it, so this height looks roughly, that's a rough symbol there, then we'll be using this symbol to be distributed as, roughly distributed as, it's normal, as far as we can tell. The dominant average is 175. And can we get like 1/3 of the data? So here we get 1/6 plus 1/5. What's that like? There to there. 20, it's like 36%. Yeah, roughly. So 15 centimeters. Roughly. Okay. So that's what I mean by summarizing this. So this thing here is the height roughly as a normal. The rough here actually is in the standard deviation. I'm only guessing it's 15 centimeters. So 175 centimeters is the dominant average, and most of the data is within 15 centimeters. So if I draw a cross at 15 either side, so it's 160 to 190. We should see 2/3 of the data there within one standard deviation. Okay, so examples of random variables that are likely to have a normal distribution. Experimental measurement. So like even if you're, so if you measure, you're going to have an error. So imagine, it's difficult really to say here. I won't spend too long on that, but in general, if you're measuring things, maybe if you look at the errors, actually, yeah, so a repeated experimental measurement, right? So imagine that you're measuring the length of a rod, different rods, loads of different rods. Particular experimental measurement, look at the errors. So when you measure the rod, on average, you should get exactly the right answer. So the dominant average is 0. But perhaps, now say you're using a meter stick, it's hard to say here, like, so I won't put in a sigma, but on average the error will be 0. But sometimes you have a positive error when you overestimate, sometimes you have a negative error when you underestimate. Snowfall, now this one is very dangerous because when we assume things are normally distributed and we make calculations and we say, oh, something only happens every 400 years, but then it's not actually normally distributed, we have a problem, a big problem. So examples of this is something like the heights of waves, where these massive mega waves are predicted to come every 50,000 years. And so like if you're building a device or a structure in the sea, a 1 in 50,000 year event, you're just not going to worry about it. But maybe it's not normally distributed, and actually these events are far more common than calculated. So the heights of women, heights of people is normally distributed. Length mass of a manufactured product. These are all good examples. But be careful. Yeah, here we go. Wave height certainly is normally distributed. Okay, so I've only just a few more minutes, see how much of this we can do. In practice, the normal distribution is very useful in that real-life calculations are very easy to handle because all normal distributions are related to each other. They all look like, they all have a bell-shaped curve. They're all rescaling of a particular normal distribution, this universal distribution, if you will. This is the normal distribution with mean 0 and standard deviation 1. So look at this one. The dominant average is 0 and approximately 2/3 of the data is within one standard deviation. All normal distributions are transforms of this. So this is called Z. So when I say Z, it'll be, it's a random variable with a dominant average of 0 and a standard deviation of 1. The actual formula for this is this. So actually what this means, is all normal distributed, the curve has this formula with the mu and the sigma, but the Z one in particular, so say, I don't know, f of Z equals 1 over root 2 pi e to the minus z squared over 2 is the formula for that, okay? So the thing is that there's a relationship between this one and this one. Any particular one, you've got this formula. You can transform from a general normally distributed one where the dominant average is mu. You can kind of center it at 0 and make the standard deviation to be 1 using this formula. So you put in the x values. Now we'll see this in practice in a later lecture, into this formula, and what it'll do is it'll turn, like the peak mu will turn to 0. If you've one standard deviation above here, will be sent to 1 here, and so on and so forth. It's transform that converts the x distribution to a z distribution. So mu, as I said, will go to 0, etc. So let's just look at that. So if I put in mu into this for instead of x, so if I put in this where the peak is, I get mu minus mu over sigma, which is equal to 0. So the peak gets sent to there. You can also transform using this. Now, often I'll be talking about what formulas are on the exam paper, but you're going to have an assignment, so there's no worry there. So z you can actually think of as the number of standard deviations, because when you're at 2, that's 2 multiplied by 1, and 1 is the standard deviation. So you can see that x is its mean plus z is the number of standard deviations. Z is negative if x is less than the peak, you'll go to a negative. If x is bigger than the peak, you'll go to a positive and vice versa. Now it's not clear why this is all true, but what this is showing is that if you want to calculate the probability that a normally distributed random variable is between two numbers, for example, the probability that the height is between these two, what you can do is you can transform this problem to a normal distribution, and instead of working with the x numbers, work with the z numbers, and it turns out that we can calculate this.